I doubt it. Yeah, well, you can fill anything out. Whether they're right is different. All right, so we've got this guy here called the unit circle. Okay. All we're going to do, so this thing, you guys remember like times tables in the second, third, fourth grade? Yeah. Okay. Some of us, maybe the second time we did it in the second grade, third grade, boys? Huh? Rocket math. What's that?
We did like the 981.
Okay. So this is ultimately those times tables for trigonometry. There's going to be a lot of procedures, and we haven't really gotten to the nuts and bolts, the fun part of trig yet, because we're learning these fundamental skills. But this is going to be something that we have to continually pull information from and use in intermediate processes and final processes in the trig stuff that we're going to do with graphing trig functions, with solving trig equations, working with polar coordinates, working with vectors. We're going to have to know from the top of our head real fast what is the sine of 21 pi over 6. Okay? And you're going to have to know almost instantly that it's negative 1. Okay? It's just something that we're going to practice. This is going to help start that process. Okay? The way that we develop this, okay, is we're going to go through and we're going to count by 30 up until 360. So this would be 0 degrees. This would be 30. This one's going to be 60. Okay. One in the middle is 45. We'll come back to that in a minute. This one's 90. 120. 150. 180. 210. 240. 270. 300. 330. 360. And you guys missed a perfect opportunity for a good mom joke there.
I was going to say that, but I have too much respect.
Okay. All right. So 0 all the way around to 360. Count by 30s, right? Do the same thing with 45. So this will be 45.
I was so confused. I didn't know my life was upside down.
You want another one?
Yeah.
Oh my gosh, can I get another one too, please? Oh my god. I hardly made this out though.
Oh, well, yeah, you. All right, so we're going to go through and now fill in the multiples of 45. So
45.
some of those are already done, right? But 45, and then we get to 90. 90 plus 45 would give me 135. This is going to be 225. And then this last one over here is 315. Okay. Another way of doing that to fill in the 45 increments is, you know, between 30 and 60 halfway. That's a 30-degree difference between 30 and 60 halfway. It would be 15 degrees, right? So take 30. So 30, add 15, I get 45. Come over here, 120, add 15, I get 135. 210, add 15, 225. 300, add 15, 315, right? Okay. Pretty easy? All right. So now that was in degrees. Now we got to do it in radians. Okay. So we already have a tool that allows us to do this in radians, but it's multiplying each of those by pi over 180, right? And simplifying. That is time-consuming and ultimately, eventually, dumb. Okay, so we're not going to do that. Can you guys count to 12?
Yeah.
Okay, that's all we're going to do. Okay, we're going to count essentially to 2 by 12. Okay, it's not hard if we understand that 2, okay, is written as 12 pi over 6, if we know that. Okay? And this is the reason that, we can use those values. Isn't 30 degrees pi over 6? Okay? So then isn't 60 degrees 2 pi over 6s? Okay, now I'm not going to reduce anything. Okay? So I'm going to keep adding pi over 6. So pi over 6, and then I add another one, I get 2 pi over 6. Add another one, you get 3 pi over 6. Okay, just humor me here real quick. What are we doing here? Pi, the numerator is 1 pi, 2 pi, 3 pi. What do you think the next one's going to be? 4 pi. 4 pi over 6. Next one. 5 pi over 6. Next one. 6 pi over 6. Next one. 7 pi over 6. Next one. 8 pi over 6. Next one. 9 pi over 6. 10 pi over 6. 11 pi over 6. And then what's that get us to? 12 pi over 6. And that's 2, isn't it? 2 pi? So getting a lot of these radians are just counting to 2 by 12s. Okay? Or making sure that I know all my denominators are 6. Okay? And then counting my numerators 1 all the way around to 12. Okay? Is that all right? Okay. I did skip some. Which ones did I skip? The 45. So what's 45 degrees as a radian? Pi over 4. Okay. Pi over 4 plus pi over 4 would be 2 pi over 4, which is at 90 degrees, which is, we already have one there, right? So you don't have to write that one. Add pi over 4 to that. 3 pi over 4, right? Then it gets me to 4 pi over 4, which we already have something written there. And then the next one is 5 pi over 4. The next one is 6 pi over 4. We already have something there. And then the final one is 7 pi over 4. If you want to, that's 8 pi over 4 as well, but we already got something there. And that is also 0 radians. Okay? Now, and I'm going to apologize for this because I didn't tell you at the beginning, I forgot. We're going to go through and we're going to reduce those, so we're going to have to erase these. Okay? Because they're never going to ask me what is the sign of, say, 8 pi over 6. They're going to ask me what is the sign of 4 pi over 3. Okay? So we're going to go through. There's only a handful of them that we have to reduce. So we go through and find the ones that we need to reduce. Nothing in the first quadrant, but this top one up here, that one right there becomes pi over 2, right? Okay. 4 pi over 6, what's that reduced to? 2 pi over 3. I'll highlight the ones that need to be reduced. Those, that one, that one, that one, and that one.
You got an eraser? Mine? That's tiny thing. I love it understanding. I can't read it.
If I wrote on pin, can I make it?
Here. What?
Can I get paper since I wrote on pin?
Yeah. Anybody else need another one?
It doesn't open.
Well, it's because you don't know how to use a stapler.
No, I want to open it this way.
It's not strong enough. You can't do that.
You're pressing a button in there.
No, I'm not.
I'm sorry. I'm going to tickle my finger, dude.
Yep. That's it.
It doesn't come apart.
You are an idiot. So,
What are you pressing?
I'm just pulling apart. You didn't go to the weight room yesterday, so. Cole?
What? Oh,
Stop.
what is it?
What if you got it in his eye?
Here, hey, back up this way.
Oh, yes, sorry, yep. All right, so as we go through that, reducing those, we should follow up with pi over 6, pi over 4, pi over 3, and then pi over 2. 2 pi over 3, 3 pi over 4, 5 pi over 6, pi, 7 pi over 6, 5 pi over 4, 4 pi over 3, 3 pi over 2, 5 pi over 3, 7 pi over 4, 11 pi over 6, and then 2 pi. If at any stage you question yourself whether you've done that correctly or not, let's say that I get to like 5 pi over 3, and I'm not sure, did I do that one right? Does that one seem correct? Take 300 pi, or 300 degrees, and multiply by pi over 180, and see if it generates a 5 pi over 3, okay? Because that's an alternative route, right? But next week when I give you this sheet again, and it is a legit quiz, and each one of those is worth half a point, and you have 7 or 8 minutes to do it, if you go through and you try to convert each one of those degrees to radians, you're not going to have time to fill in the ordered pairs. Okay? So the idea is, can we do this efficiently and quickly? Eventually then, what's going to happen is that this circle, through a collection of different data points, and I'll explain how we do this later on, is going to turn into that curve right there, okay? And the x-axis eventually is going to be written in terms of those radians or in terms of those degrees. Does that make sense? So we have to be able to eventually, when we get to this, go through counting from 0 to 2 pi by sixes like that, 12 times, okay, to structure that graph, okay? So that becomes a process that's very, very important to us, okay? Now, yesterday we spent a bulk of the time discussing these ordered pairs, right? Okay? If we look at this ordered pair here for 0 degrees, the x value is 1 and the y value is 0, right? So we're just reminding ourselves we are in the coordinate plane here. Excuse me. We're in the coordinate plane. So from that point right there, which is 0, 0, we would have to travel 1 unit to the right and then up nothing to get to that point. Okay? If you remember our 30, 60, 90 triangle that we drew here, with that being 30 degrees, okay, hypotenuse being 1, we worked out this length being 1/2, this length being root 3 over 2. So to get from, again, the origin to that point there, you travel x direction of root 3 over 2, and then a y direction following that of 1/2. You guys remember doing that a little bit yesterday? So that's the ordered pair that is on the circle that is attached to a 30-degree angle on that unit circle. The next one is a 45, 90 degree triangle. And that gives me root 2 over 2 as the x distance and root 2 over 2 as the y distance, because that triangle is ultimately isosceles. So the x's and y's, or the legs of that right triangle, are the same. And now those are really the only 2 points that you need, or that maybe you're not accustomed to so far, to fill in the other remaining things on this entire chart. Okay? Because every 45-degree angle, every multiple of 45 degrees, except for the quadruple, except for the 90, 180, 270. So all of these red ones here that I'm highlighting are going to have the same ordered pair. Radical 2 over 2, radical 2 over 2. Okay? We'll have to pay attention to the plus or minus of it, but they should all be the same. Okay? Every other point on there is either root 3 over 2, 1/2, or 1/2, root 3 over 2. And this is the reason. This line here was, well, y equals x, right? from yesterday? If I take and reflect that point over line y equals x, it becomes that one. And if you guys remember back from college algebra, if you have a comma b as a pre-image, and when we reflect across line y equals x, you get b comma a, right? So doesn't it make sense at this point here? It would be 1/2, and then root 3 over 2. We good with that? And then what's that one up top going to be? 0, 1. Okay. And now yesterday we introduced this concept, but the bell rang. When we reflect across the y-axis right here, reflect across that purple line, okay, distances are preserved. So that means this point right there, however far away from the y-axis it is in a horizontal distance, that distance is going to be replicated over there. Does that make sense? Okay. So that solid purple line, horizontal line is going to be the same length as that one. That is the x direction, isn't it? So to go from, and this is where people forget that we're in the coordinate plane, to go from 0, 0 to that point right there, I got to move to the right 1/2, right? And that gets me under the point, and then I got to move up radical 3 over 2. Well, if I want to go to this point, now I need to move left 1/2. So it's got to be negative 1/2. And then because distance is preserved, then the distance that I travel vertically right there would be the same as the distance that I travel vertically there. So it's going to be root 3 over 2 again. And because they're both moving up, they're both positive. So root 3 over 2. Okay? So that practice of reflections and understanding the logic behind reflections and the algebra and all that kind of stuff that takes place with reflections is going to tell me that this point here is going to become that one, right? Does that make sense? Okay. So root 2 over 2, root 2 over 2, but the x value is now negative. And then finally, in the second quadrant, that ordered pair is going to be that one. So I have root 3 over 2 and 1/2, but the x is negative. Okay. Just remember, every point in the first quadrant is positive. Every point in the second quadrant is negative, positive. And that should help you remember that these signs, these x values, have to be negative. Pi is going to be negative 1, 0. All right, now that you have those, okay, take a minute on your own and reflect those from the first and second quadrant, reflect them into the third quadrant. Okay, so just get you a start here. This one at 5 pi over 6, what point or what value down here is that going to fall on top of when we reflect? 7 pi over 6. So 5 pi over 6 and 7 pi over 6, they have to have the same coordinate. But in the third quadrant, they're both negative. So as you fill that in, I'll fill mine in. the idea then, once you have that filled in, the idea on homework and stuff like that, having that chart in front of you is going to be nice, okay? Allows you to generate things quickly, and even as we, work in 6-1 and 6-2, that's going to be great to have in front of you. You can pick off answers and values real quick, but eventually, what you're going to want to commit to memory. Well, I'll draw it on that screen. Draw it on that screen so we can get on tape here. Eventually, what you're going to probably maybe on tests and quizzes put at the top of your page is the first quadrant. You'll put an arc in. You'll say pi over 6, pi over 4, pi over 3, pi over 2. You'll say 0, 1. Okay, this one's going to be 1/2 root 3 over 2, root 2 over 2, root 2 over 2. Next thing is going to be root 3 over 2, comma 1/2, and maybe you even got 0 here, and you put 1, 0. And if you can remember that quadrant, the other quadrants are just a reflection of that, right? Okay. So eventually, hopefully, that entire unit circle dwindles itself in your brain down to just that quadrant. Okay. But for efficiency purposes right now, and just to make sure that we understand what's going on, we're going to work with the whole circle. I'm going to quiz you over the whole circle. But what I want you guys to do real quick, just kind of follow along. If you want to use your calculator, you can. But all I'm going to do is, and I did this in the last class, but I'll delete it, kind of show you if you want to do this on your own, how you would do this in Desmos. So Desmos has and GeoGebra is the same way. They have the ability to do a little bit of coding, a little bit of programming, so we can see relationships a little bit easier. So what I'm going to do here real quick, and we can do this in degrees or radians. I believe right now I'm in radians, okay? So I'm going to say, I'm just going to ask, what is the cosine? Let's do this real quick, just so we have some numbers up here that make sense. So square root of 3 over 2 is that number. Square root of 2 over 2 is that number, okay? So as we work with evaluating the cosine function here at some angles, if we get these numbers, we know we're getting back radical 3 over 2 or radical 2 over 2, right? Okay. So I'm going to figure out what cosine of A is. And I ask you to create a slider for A. So here's where we can do some of the coding. I can click on here and I can say I want A to go between 0 and 2 pi. And I want it to step by pi over 6. So all that means is, like as I move over one time here, it goes by an interval of pi over 6. That would be 2 pi over 6, 3 pi over 6, so forth. Does that make sense? Okay. Just to maybe see what because A right now is in radians. If I wanted to see what that was in degrees, maybe I can go A times 180 over pi, and now you see that either 0.523 radians, or which is pi over 6, or 30 degrees is being put in for that A right there. Does that make sense, everybody? Okay. Now, when I evaluate at 30 degrees or pi over 6, we're getting back 0.866, right? Well, 0.866 was root 3 over 2, correct? Yep. Is that number right there for the 30 degrees or pi over 6? Okay. If I go to pi over 3, okay, so you see this is pi over 3 as a decimal, 60 degrees, right? Evaluate the cosine at that, and you get 0.5 back. Is that the 0.5 that is attached to 60 or pi over 3? Does that make sense? If we go one more, pi over 2, so that's pi over 2, 90 degrees. You see you get that cosine value back, right? Cosine evaluated at pi over 2 is that x coordinate. Let's just try 2 pi over 3 real quick. Okay, so we see it's 120 degrees. That as a decimal, or 2 pi over 3 as an exact value. What's the evaluate for the cosine? -1/2. Is that okay with everybody? So what is it? What is the argument here? What do you think all of these x values represent on the unit circle? The x values are all the cosines of those angle measurements. Okay? So each one of those. So if I ask you, what is the cosine of 4 pi over 3? Cosine of 4 pi over 3, -1/2. If I ask you, what's the cosine of 5 pi over 3? +1/2. Cosine of 5 pi over 6? -√3/2. That kind of make sense? Allows you to get those values as exact values much quicker and efficiently than even grabbing your calculator. Okay? So what do you think the sine is? The y value. Okay, so if I say, what is the sine of 7 pi over 6, you're going to tell me it's -1/2. It's the y value of -1/2. Okay? And we're going to talk in a lot more detail about that and how that and why that is true. But I think it's important to see, what is this tool going to do for us? Why are we making this? What I want you guys to remember, and we did this with domains and ranges. Remember, if I talk about domain, range, x, and y, domain and range are alphabetical D, R, right? X's and Y's are alphabetical respectively to one another, so X and Y. So you remember doing that and say, okay, well, domain then has to be the X values and range has to be the Y values? Which one comes alphabetical first, cosine or sine? Cosine. So cosine and sine, again, play on that alphabetical relationship. And now you can remember that on these ordered pairs, the X value is your cosine, the Y value is your sine. Okay? That's not intentional. It wasn't structured that way. I mean, I don't know if I told you guys that sine is actually referring to your sinuses in your head. Okay? When this math was first being done, it was done in language A. It was then translated to language B, and then translated to language C. And through that translation, something went amiss. And what it was initially referring to, which I'll show you eventually with a geometric graphic, what it was initially referring to got translated unintentionally to sinuses in your face. So, kind of stupid, but. Okay. However, let's do this real quick. Let's just kind of mention some relationships here. And we'll talk in a lot greater detail about this. But what is off of this information, what is the cosine? Let's do this. Sine is easier. Let's go sine of 30 degrees. Tell me what the sine of 30 degrees is. 1/2. Okay. What is the cosine of 60 degrees? 1/2. If I look at those two things, aren't those equal? So doesn't that mean this is true? Okay. What do you notice about that angle measurement and that angle measurement? They're complementary. And there's where we get the relationship sine and cosine, right? Co representing complementary. So if I were to tell you sine of 30, or not sine, let's go sine of 35, you're going to tell me that's equal to cosine of
90 minus 35.
90 minus 35. 55, right? 55. Okay. And that's, I like how you said that because that's how that is actually introduced, is that, and you maybe saw this on the geometry in a course exam, okay, because this is a common question. It's if sine of A equals cosine of what? And they say 90 minus that. Okay. So that's a relationship that we can hopefully recognize and justify through the use of the unit circle here. All right, so that's a tool that I want you guys to use. I want you to have it in front of you. I want you to have access to it. But by mid next week, we are going to use that from memory. Okay, I'm going to quiz you over it. Okay, but this is what they're going to be asking you to do with it. Okay, so they're going to ask you find the terminal point with these t values. Okay? And remember, t-value, that is the length of the arc, or because we're in a unit circle, it's the measurement of the central angle. Okay? So however you want to view it. Negative pi over 4. Now, here's the thing. I don't want to do negative pi over 4 because we don't have a unit circle right now written for negative pi over 4. If I was going to do a unit circle for negative pi over 4, we would have to do this. You would have to say that this is negative pi over 6, negative pi over 4, negative pi over 3, negative pi over 2, negative 2 pi over 3, negative 3 pi over 4, all the way over, right? Okay? Nobody wants to do that, right? That would basically mean you need a unit circle for positive values going counterclockwise, and you need a unit circle then for negative values moving clockwise. We don't do that. We don't like that. Okay? But if I'm at negative pi over 4, okay, and let's say I travel that direction and I go that far, does it get me back to negative pi over 4? How big would that red arc be that I just drew? Or how big would be the angle that would have been traced out with that red arc? 360, but in terms of radians, it would have been 2 pi. So can I take negative pi over 4, and instead of dealing with it as a negative pi over 4, can I add 2 pi to it? And get me a coterminal spot, right? Coterminal point. So I'm going to add 2 pi to it. Now, I want to do this all year long. Okay? From here on out. Every time I deal with 2 pi, I'm going to deal with it in an efficient, convenient way. I'm not going to write 2 pi here. I'm going to write 8 pi over 4. Still 2 pi, right? Okay? So that gives me t to be positive 7 pi over 4. Now, look at your chart. What's the coordinates for 7 pi over 4? That order pair, right? So my question then, what is the cosine of 7 pi over 4? Radical 2 over 2. So now think about this. These two numbers, negative pi over 4 and 7 pi over 4, those points are the same. So now the question is, what is cosine of negative pi over 4? Cosine of negative pi over 4, that number right there, it's radical 2 over 2. Does that make sense? Because it's the same as the cosine of 7 pi over 4, because they're the same point. Yes?
We want to take notes on the back of this.
It's yours. The next one, 3 pi over 4. Okay? Look at my unit circle. Excuse me. Unit circle, 3 pi over 4. What's the order pair that goes with 3 pi over 4? Three pi over 4. 3 pi over 4. Isn't it radical 2, negative radical 2 over 2, count radical 2 over 2? Okay. Negative 5 pi over 6. What should I change that to? It's negative. So let's add 2 pi to that and make it positive, right? So 2 pi in terms of 6s would be that. And that gives me 7 pi over 6. And a terminal point with 7 pi over 6. Is it that? That makes sense? So my question, if I were to take my calculator and type in sine of negative 5 pi over 6, what's it going to spit back to me? Negative 1/2, okay? This is the cosine of 7 pi over 6, which is the same thing as the cosine of negative 5 pi over 6, right? This negative 1/2 is the sine of 7 pi over 6, which is the same thing as the sine of negative 5 pi over 6, okay? So that's, now eventually, it's like your times tables, okay? Maybe when you first did your times tables and they did 3 times 8, you had to do, okay, well, that's 3 plus 3 plus 3 plus 3 plus 3 plus 3 plus 3, and added those up, right? Right now, we maybe have to do it a little bit slower, but eventually when I say negative 5 pi over 6, you think, okay, right away, radical 3 over 2, 1/2, and then make them both negative. And that will be something that you guys can do quickly. Now, If you never look at this again, you never use this again, are you going to be able to do that? No. Okay? So you're only going to be as good at using this as, it correlates to how much you invest in it. Let's do this one. Let's go, so those were negative. Let's say that t is equal to 21, let's go 22 pi over 6. 22 pi over 6. Now, is that bigger than 2 pi?
Yes.
So that's more than one rotation, because 2 pi, in terms of sixes, is that, right? Okay. So what I'm always going to do is I'm going to look for a t value that is between 0 and 2 pi, because that's what my unit circle is defined for, 0 to 2 pi. So I'm going to subtract 2 pi. And it gives me 10 pi over 6, right? Does that reduce? 5 pi over 3, right? Now 5 pi over 3, okay, is going to be the ordered pair. What is it, 1/2 negative root 3 over 2? Okay. Now, when I do that, okay, when I ask, what is the ordered pair for 5 pi over 3, I'm not thinking about 5 pi over 3. I know what quadrant it's in, because it's pretty close to 6 pi over 3, right? It's one more 30 degrees from 6 pi over 3, or 60 degrees from 6 pi over 3. I know it's going to be in the fourth quadrant. When I look at 5 pi over 3, I'm not thinking about 5 pi over 3. I'm looking at pi over 3. I know what pi over 3 is right there in the first quadrant, right? I know that order pair for pi over 3 is 1/2 root 3 over 2. Okay? And then isn't 5 pi over 3 the reflection of that into the fourth quadrant? Does that make sense? Okay? So that's what hopefully is going on in our minds when we're doing this. And this next process is hopefully going to kind of force that to happen. Okay? So we'll talk about this for a brief moment. This is, you guys are going to talk about theta bar. Theta and theta bar, your reference angles back in chapter 5. Same thing. They just now call it a reference number. Okay? But they call it a number because it's a distance. They're talking about this arc. But we can make the connection that theta, the angle that is, so if I put a ray in here through that terminal point, okay, that theta is the same as that t, right? Okay? If I put a ray through right here, okay, the theta would be the same thing as that t. If I want to figure out what a reference number is, it is the distance that we need to travel from our terminal point to get to the x-axis. So if my terminal point is right there, I need to get to the x-axis, the shortest distance to get to the x-axis. So does it make sense that I got to travel back that way?
Yeah.
So if you're in the first quadrant, your reference angle or reference number is trivial. They're the same thing. T and T bar are the same thing. Okay? But if I'm in the second quadrant, if this point here terminates in the second quadrant, the distance to get to the x-axis, the shortest distance, would be that right there, right? Okay? So that T bar is found by taking pi minus T. Pi minus T will get you that distance. Now think about this. If I told you T was 5 pi over 6, T bar, so 5 pi over 6 would be right here. How big would T bar be if I need to get to 6 pi over 6? It'd be 1 pi over 6. Now here's why we call this a reference number. The ordered pair for 5 pi over 6, now because of symmetry, the ordered pair for 5 pi over 6 right here, this purple dot, is going to be the same as the ordered pair of pi over 6. Does that make sense? Because with symmetry, if I follow the y-axis, doesn't that point go right there? And that's pi over 6. Okay? So that ordered pair for 5 pi over 6 is going to be the same as the ordered pair for pi over 6, except for 5 pi over 6, the x value is going to be negative, right? This is in quadrant 2. Okay? So it's how we find those reference numbers. Now, in the third quadrant, if my terminal point is there, to get back, T bar is going to be T minus pi. Okay? I don't necessarily like these formulas and use these formulas, but if you want them, they're there. We'll do some practice problems on Monday that hopefully you'll see I don't need. So if this one's 7 pi over 6, Then I know that's still 6 pi over 6, right? How far back do I need to go to get from 7 pi over 6 to 6 pi over 6? 1 pi over 6 again, right? Okay. So I like to do it that way. It is still subtraction, but I don't physically do the subtraction on my paper. This last one is if you're in the fourth quadrant, the reference is going to be 2 pi minus t. Okay. And what I like to do then is, let's say I'm at 7 pi over 4. I don't go 2 pi minus 7 pi over 4. I ask myself, how much further do I need to take 7 pi over 4 to make it 8 pi over 4? Because that's 2 pi, right? So 7 pi over 4 to 8 pi over 4 is how many?
1 pi over
1 pi over 4. And there's my reference numbers. Okay? Your homework, okay, there is an assignment going to be posted here in a moment. Not due on Monday. It'll be due like Wednesday-ish. Don't pay me, because I haven't given you homework all week. Okay? So when you're doing this, there's going to be a series of questions that say find the terminal point. There's going to be a series of questions that say find the reference number. And then there's going to be a series of questions that eventually say find the sine or cosine of 7 pi over 4 using this whole process. Okay? So they're going to try to build you up through that. Not due Monday, but this should give you a start in regards to addressing that stuff.
Can we compromise and make it just Thursday since the juniors have the